morning class and welcome to our course in Sustainable Energy Technology. Today we will start our discussion on hydrogen and fuel cells. As we discussed in the previous class, hydrogen is a very important and emerging energy storage technology, specifically chemical energy storage technology, on which a lot of effort has been currently put to make it economical and successful commercially in bulk. The reason why hydrogen is so important is that it is an extremely versatile zero carbon fuel. It is not a primary fuel because hydrogen is not available in significant quantities on Earth naturally. So it has to be produced from other sources. As we will show, typically hydrogen has been produced from fossil fuels, which obviously also emits CO2. So renewable hydrogen, or green hydrogen as it is called, is usually produced from renewable electricity like electrolysis of water through renewable electricity. This hydrogen then becomes a way to store renewable energy within hydrogen as a stored chemical compound. Then this produced hydrogen can be used in a fuel cell device to regenerate the electricity in times of high demand or in a distributed system or inside a fuel cell powered vehicle, and in this way the energy can be recovered. This figure here kind of shows the basic idea of how hydrogen can be generated and utilized. Suppose you have wind energy or solar energy. The electricity from wind and solar energy is used to break up water to form hydrogen and oxygen. The hydrogen is stored in large tanks like this shown here, and then it is transported to the place where it is going to be utilized. It may be an industry where the hydrogen can be directly burned to generate process heat for many industrial applications, or it can be sent to a hydrogen to a center where fuel cells exist, and that fuel cell converts hydrogen to electricity and sends it back to the grid. Alternatively, hydrogen can be directly loaded into a fuel cell vehicle or a truck or a train where hydrogen is converted into electricity and then into motive power of these transportation engines. Another alternative is to produce a direct hydrogen burning combustion engine like a hydrogen IC engine, and that can be fitted to a vehicle as well. As we can see, then hydrogen is an extremely versatile source of energy from which you can generate electricity, or you can directly burn to produce process heat or run engines or other types of transportation devices. So let us look at some of the properties of hydrogen that make it good as a chemical energy storage material. The first point of note is hydrogen is a zero carbon fuel. Its molecular composition is H2, it does not have carbon in it. Hence, the utilization of hydrogen does not produce CO2 or other greenhouse gases. It is a fuel, so it can be directly burnt in furnaces, power plants or engines to generate heat, electrical power or motive force instead of fossil fuels. So instead of say natural gas, which will still generate CO2, you can burn hydrogen directly in a gas power plant, for example, or in a furnace to generate industrial heat, or instead of a compressed natural gas running engine, you can have a compressed hydrogen vehicle where the compressed hydrogen is being burnt in an IC engine kind of a system to run cars, trucks, ships, etc. Alternatively, There is a device called fuel cell, which we will also discuss in detail later in the class, which can convert hydrogen directly into electricity with very high efficiencies. Hence, you can also convert hydrogen to electricity without having to go through the combustion process, which can produce pollutants like NO2, etc. The overall reaction is hydrogen reacting with oxygen to produce water vapor and energy. Since free hydrogen is rare on Earth, it has to be generated from other sources. Hydrogen generation without CO2 emissions require the use of renewable resources like biomass or renewable energy like renewable electricity. So you can convert biomass, which is a renewable energy resource, directly into hydrogen, or you can use renewable electricity from a solar power farm or a wind farm and use the renewable electricity to electrolyze water to produce hydrogen. Current focus is electrolysis of water to generate H2 using renewable electricity. In such a case, hydrogen becomes a chemical energy storage medium in which the energy from electricity is being stored. The current status is hydrogen production, storage, transportation and utilization is expensive due to technological challenges. This is especially true if you are using renewable means to produce hydrogen. Hydrogen from production from hydrocarbons like coal, natural gas is relatively easier than hydrogen production from renewable sources like electrolyzing of water or hydrogen from biomass. Hence, the cost goes up at the current technological status. So, there is a lot of R&D going on improving the electrolysis technology or the biomass to hydrogen conversion technology to increase their effectiveness and decrease their costs. Another problem is the round trip efficiencies are currently low, around 30 to 40%. This is lower than most other types of energy storage systems. We will see why the round trip efficiencies are low later in the class. So, decrease of cost, increasing safety, and safety is also an important concern because hydrogen is a very light and extremely combustible and explosive gas. So, there is significant explosion and leakage hazard while producing, storing or transporting hydrogen. So, a proper hydrogen infrastructure must take into account the safety concerns that hydrogen naturally brings. So, decrease of cost, increasing safety and improving the round trip efficiency are the focus of current technological research on hydrogen energy. Now, first we will discuss the various ways to produce hydrogen from renewable resources. And there are many ways that are currently in play. The most common method and most talked about method is direct electrolysis of water using renewable electricity. Here you can use liquid water and electrical energy from renewable resources as the source of energy and break water to produce hydrogen. Another option is instead of water you use steam. In this case you can use a bit of thermal energy to help break up the water molecules, and so less electrical energy is needed. This thermal energy can come from a CSP, concentrated solar power system, or waste heat from an industrial system, etc. So if a thermal energy source is available, it can convert water into steam and improve the electrolysis efficiency process. Another method is photocatalysis, where you are using a catalyst and breaking water using the energy of light directly. So here electricity is not being used, but light energy is directly being used to convert to break up the water molecules using a suitable catalyst material. So you are basically bypassing light to electricity step through a solar panel, for example. So this is potentially a way of direct capture of light energy into hydrogen without going through the electrolysis, solar electricity generation and electrolysis route. But there are certain challenges. Catalyst efficiency is a problem, conversion efficiency is a problem. So this is still in the research and development phase. Then you have photoelectrochemical water splitting. Here a combination of electricity and light is being used to electrolyze water, again usually in the presence of certain catalysts and other materials. So here part of the energy comes from light and part of it comes from renewable electricity to electrolyze water to produce hydrogen. Another option is using biological medium like microbes which can break down water molecules in the presence of light, and this is called biophotolysis. So microbial reactions in cells of microbes in the presence of light energy can break water to produce hydrogen. Again, a very promising route, but here there are issues of improving the microbe efficiency and increasing the speed of production, because usually biological routes are much slower than what we would need for industrial scale hydrogen production. Then you have thermochemical water splitting. Here the source is thermal energy, may be obtained from solar thermal plants, or trapping the light of the heat of the sun, or from geothermal energy, for example, right? Waste heat can also be a source, industrial waste heat. So here the heat is driving chemical reactions in the presence of catalysts again to do the water splitting. So here electricity is not being used, thermal energy is directly used in presence of certain catalysts to break down water into hydrogen. All of these are water to hydrogen production routes. Another way of producing hydrogen is from biomass sources in renewable way. And here you have two main types: anaerobic digestion, where microbes are used to break biomass molecules to produce hydrogen in an oxygen-free environment. So this process energy uses biochemical energy. The energy of the microbes in the absence of oxygen within certain anoxic tanks primarily digest the biomass, and while they consume the biomass, they release hydrogen as a byproduct. Okay. So that is anaerobic digestion route. Then you have a purely thermal route of gasification, where the biomass hydrocarbons are partially oxidized in the presence of air and steam to produce carbon monoxide and hydrogen, and then the carbon monoxide is converted to CO2 in the presence of water vapor to produce more hydrogen through what is called the water gas shift reaction, and the final product there is CO2 and hydrogen with a bit of water vapor, methane, etc. Here, even though there is a release of CO2, because the source is biomass, a renewable source, there is no net CO2 generation during the process. So those are the various means by which you can get renewable hydrogen from either water or through from biomass through digestion or gasification. So today I will end this short section, and we will cover hydrogen in more detail later in the week. We will discuss hydrogen production through electrolysis. So here we are splitting water and using electricity primarily to split water. This is the electrolytic cell. You have again two electrodes, a negative electrode and a positive electrode. In an electrolyzer system, the negative electrode is the source of electrons, and hence it's called the anode, and the positive electrode is the sink of electrons, and hence it's called the cathode. Here what is being done is electricity is entering the system and is used to drive the reaction, splitting water into hydrogen and oxygen. Typically what happens, water is being consumed clearly. So fresh water is added into the electrolytic cell, which gets continuously converted into gaseous hydrogen and oxygen, which are being captured as they flow out of the electrolytic cell. Inside you have an electrolyte, for example a sulfuric acid solution or a potassium hydroxide solution, and H plus ions are transported through this electrolyte system. So in the negative electrode, what happens is the main water splitting reaction happens, energy is consumed to break two molecules of water in liquid state into gaseous oxygen and 4 H plus ions. So H plus ions, 4 atoms of H plus ions are produced and 4 electrons are produced, and these electrons are going into the system, into the external circuit. Then at the positive electrode, these 4 H atoms are entering the positive electrode along with 4 electrons that are coming from the external circuit to produce 2 molecules of gaseous hydrogen. The reaction with the negative electrode, the anode, is energy consuming. So there is a negative potential gradient here. Reaction of the positive electrode is neutral. So this has 0 potential gradient here. And there is a transport of H plus ions from the negative electrode to the positive electrode, completing the circuit. So external circuit, electrons are moving from minus to plus. And in the internal circuit, H plus ions are moving from the negative electrode to the positive electrode to generate hydrogen. So cold water electrolysis is the first type of electrolysis system. Is the first type of electrolysis system which occurs at normal temperature and pressure. So here we are not increasing the temperature and pressure, it's just liquid water. Liquid electrolytes like potassium hydroxide or sulfuric acid can be used to conduct the ions through the solutions. Alternatively, solid polymer electrolytes in the form of proton exchange membranes called PEMs, like Nafion, it's a kind of a specialized moist polymer type electrolytes that can transport ions through it. This Nafion is a kind of a prototyped polymer exchange membrane. Its primary constituent is it's kind of a sulfonated tetrafluoroethylene. Tetrafluoroethylene is a typical kind of a polymer, and it's a sulfonated tetrafluoroethylene, and the trademark name is Nafion. It's a type of a proton exchange membrane which allows the transport of protons through them. Okay. The electrodes are usually plated with the platinum catalyst to increase reactivity. So usually if you are having to drive these reactions in normal temperature, you need a noble metal catalyst like platinum to increase the reactivity of the system. And the energy efficiency of the process is around 55%. So 55% of the energy that the external electricity is giving, that 55% of the energy is being converted into and stored as hydrogen molecules. Another option is high pressure electrolysis. So the operating temperature and pressure of the electrolyzer is higher than the ambient. We are still dealing with liquid water, but it's pressurized hot liquid water. Okay. So pressurized hot liquid water is sent to the electrolyzer, and pressurized hydrogen and oxygen gases are obtained. The entire system is pressurized and heated. This reduces the energy required for pressurized hydrogen storage because you are getting pressurized hydrogen as output, so you don't have to spend so much energy to compress hydrogen further and put it in cylinders. You have to compress it, but still not as much. Okay. And also part of the energy for the electrolysis is obtained from the elevated pressures and temperatures, so electricity consumptions are lower. So this is called high pressure electrolysis because you are pressurizing and heating up the system, and part of the heat is being used to convert to break up the water into hydrogen and oxygen. So less amount of electricity is required and you are getting pre-pressurized hydrogen and oxygen streams. So the requirement of compression energy is less. Then you have high pressure steam electrolysis. So this is the completely you are increasing the temperature and pressure to very high values, and water has been completely converted into pressurized steam using thermal energy. The steam is fed into a solid oxide electrolyzer cell, SOEC, solid oxide electrolyzer cell, where the electrolyte is a solid oxide material. So in this case, there is nothing liquid, and instead we use a solid oxide material as electrolyte, and the electrodes are ceramic material complexes called cermets. So here a very different kind of a cell is being used. A solid oxide electrolyzer cell is being used, and the electrolyte is a solid oxide material called cermet. It is basically a solid oxide fuel cell run in reverse. We will discuss a solid oxide fuel cell SOFC later in the class. This is basically a reverse solid oxide fuel cell. It's called a solid oxide electrolyzer cell, where the electrolytic medium is a solid oxide material, and the electrodes are ceramic metal complexes called cermets. And the operating temperatures range from 500 degrees centigrade to 850 degrees centigrade. So very high temperature. So you need an external source of heat, probably from a renewable source. The advantage is precious metal catalysts are not needed. You do not need platinum or other noble metal catalysts. You are using cermets after all. So the cost of electrolysis is lower, and efficiency is also higher. Around 80% efficiency are obtainable, and part of the energy is obtained as heat. So you are getting both higher efficiency, and you need to use less of the electricity, because a lot of the energy is coming from the heat that is available in the system. But yes, you need to give that heat. So solar thermal systems or hydrothermal energy, hydrothermal gases may be a good source of heat from which hydrogen can be produced under these conditions. Okay. So we will continue our discussion of hydrogen production and other means of hydrogen production in the next class. Thank you for listening, and we will meet again in the next class. Thank you.